Okay, let's get started. As usual, we'll come back to this problem at the end of class. First of all, course announcements. Problem set 2 will be released soon. I wanted to ask everyone, and I realize that some people might not be here partly for the reason that I'm going to ask about. There is the Iclear deadline for those of you who are in machine learning. Some of you may be involved in submissions to Iclear. Is there a general feeling like the deadline for the P set should be after the Iclear deadline? I was thinking of making it be 3 weeks until it is due instead of 2 weeks, so that it would not be due exactly on the Iclear deadline. What are people's thoughts? The Iclear deadline is October 2nd. The decision would be between the deadline of October 2nd or October 9th. It would just push everything back. It would push all the other deadlines back. Okay, so does anyone else have an opinion about this? Does anyone else want it pushed back? I know that at least one other person in the class. So I think that I will probably do October 9th, given this. There's quorum for pushing it back a little bit. However, Vincent has prepared an optional list of practice problems. So if you really want to, so first of all, you can submit it early. You should feel absolutely free to. I'll release it in the next few days. So you will be able to get started on it as early as you want. And you can submit it before October 9th. But if you want to sink your teeth into something else too, Vincent has prepared an optional list of practice problems, which he's going to hand out, where we can give you feedback on your solutions, but they're not required, and they will not count towards a grade. That's if you want practice on, these are somewhat easier than the problem set, the problem sets, and this just basically if you want additional, additional practice on proofwriting and problem solving. And those are totally up for discussion during office hours and so on. Okay. Would it be possible to have problem set 3 released before the October 9th deadline? I can certainly try to have problem set 3 released a little bit earlier so that if you complete problem set 2 early, then you can finish it. Then you can start problem set 3 a little bit earlier too. Okay, I will post about this in the Slack, and it will be on the problem set itself. Cool. And that way also you can have Thanksgiving long weekend, which is October 10th through 12th, without having a P set hanging over your heads right afterwards. Okay, let's get started. So this class is going to be on combinatorics, which is about how to arrange things. Let's start out with something that really comes up a lot in the context of arranging things, which is factorials. So the factorial is defined in this way. If you have an integer n that is greater than 0, then the factorial is n times n minus 1 times n minus 2 all the way down to 1, the product of all the integers up to and including n. If n is 0, we're going to define 0 factorial as 1. That is a separate definition, but it will be extremely useful. We'll see why in a few slides, why it is important that 0 factorial is equal to 1. And it turns out that this is just the mathematically correct definition. There's a more general theory behind factorials. This will become also relevant in Taylor's series. 0 factorial should be 1. So yes. There's also the generalization of the factorial called the gamma function, but anyway. So the first few factorials in this way are 0 factorial is 1, 1 factorial, which you get by multiplying by 1, 2 factorial, which you get by multiplying by 2 to get 2, 3 factorial, multiplied by 3, 4 factorial, multiplied by 4 to get 24, 5 factorial, 120. And then by the time you get to 10 factorial, it's really freaking big. Factorials get big really fast. This is something that you should remember. So in general, n factorial is going to be a pretty large number. Yeah. Rearranging things. How many different ways are there to arrange n different things in a list? Yep, n factorial. Y is the number of ways n factorial. N factorials always make punctuation really tricky. Like if I hadn't put the space there, it would have been really difficult to parse the punctuation. Yeah, so suppose the things are labeled as x1 through xn. An example arrangement for n equals 6 is this. This is some permutation of the 6 things. So here's x4, 3, 6, 5, 2, 1. Then there are n options for where to put x1. You can put it in any of these 6 slots. Once you've put x1 in one of those 6 slots, you know that there are 5 remaining slots. N minus 1 places left to put x2. You put x2 in one of those slots. Now after that, there are n minus 2 places left. In this case, 4 places left to put x3, and so on. So there are n possibilities for the place of the first object, n minus 1 for the second object, n minus 2 for the third object, and so on. And finally, once you've arranged all but one of the objects, there's only one place left to put the last one, and so that's the 1 here. So it's n times n minus 1 all the way down to 1, and that's n factorial. If you have 0 objects, 0 factorial is 1, means there's one way to arrange 0 objects, which sort of makes sense too. Okay. Now, how can we actually use this stuff? To do that, we're going to have to define binomial coefficients. For non-negative integers, n, k, with k less than or equal to n, we define n choose k. This is how you read this symbol. Now, if you're in LaTeX, what you're going to do is you're going to do binom nk, which I just sent out to the chat. That's how you would write it in LaTeX. But again, you're going to have the LaTeX from the slides. So this is n choose k, and that's the number of ways to select a set of k things from a set of n things. So if you have k things, you can take n things, you can take k of them. And this is without replacement. We will soon see why these are called binomial coefficients. For example, 3 choose 2. How many ways are there to select 2 elements out of the set A, B, C? Well, we can take AB, AC, or BC. So 3 choose 2 is just going to be equal to 3. Yes, these are unordered. But we'll get to that in a bit. If you are allowed to order these, if you care about the ordering, if BA is different from AB, then you're going to have something different. Okay. Some observations. N choose 1 is always n, because if you have a set of n elements and you're trying to pick one of them, there are definitely going to be n options. N choose 0 is always 1, because there is only one set with no elements at all. This is called the empty set. We're not really going to go into set theory, but there's only one set with nothing in it. It's called the empty set. N choose n is also always 1, because there's only one choice for how to choose all of the elements of the set. In this case, that would be ABC. 3 choose 3 is 1. Okay. formula for binomial coefficients. How can you work them out without just sort of exhaustively calculating everything? How can we calculate n choose k more quickly than just counting all the possibilities? So let's go back to permutations. We can pick a k element subset by permuting the n things and then picking the first k. So for example, here is a set of 6 things. Let's permute them. If we're trying to pick 3 of those things, we can just take the first 3 after we've permuted. Now, how many ways are there to do this? There are going to be n factorial permutations of the n things. We know that already. The answer isn't going to be n factorial. So like if we just took the first 3 out of this permutation, we'd say, oh, there are n factorial different choices, but we're double counting a bit. Why are we double counting? We don't care about the order of the things that we pick. If we permute those things, that gives us the same set. How many different ways are there to permute the things that we picked? Well, there are k things that we picked. There are k factorial ways to permute the things that we picked. So we're double counting by a factor of k factorial. For each of the n factorial permutations of our 6 things, there are k factorial permutations of the k things that we took that we don't care about. But we also don't care about the order of the remaining things. There are n minus k factorial ways to order them because there are n minus k remaining. So here, we can permute the remaining things, and we also don't care about that. So overall, n choose k, the number of ways to pick this set of 3, is going to be the total number of permutations, 6 factorial, or n factorial in general, divided by the number of permutations of the things we picked, divided by the number of permutations of the things we didn't pick. N choose k is n factorial over k factorial times n minus k factorial. Are there any questions about this? There are other ways to see this as well. And we're going to see, in general, just a lot of different interpretations of these binomial coefficients. None of these things will be truly hard, maybe, but just making the connections between these different representations of these ideas is really, really useful, because these will turn up in lots of subtle ways. So here's this formula. We'll come back to the term binomial to answer the question. Some examples of this. Remember, we wanted to know that n choose 0 is going to be 1. So for example, 10 choose 0 is 10 factorial over 0 factorial times 10 factorial. And because 0 factorial is 1, this is just 10 factorial over 10 factorial, which is 1. This is one of the reasons why 0 factorial really should be 1. Because we don't have to have a special formula for it. 10 choose 10 is also going to be 1 because it's 10 factorial over 10 factorial times 0 factorial. 10 choose 1, which we would expect to be 10 because there are 10 ways to choose one element out of a set of 10, is going to be 10 factorial over 1 factorial times 9 factorial. So why is that equal to 10? Well, 1 factorial is just 1. 10 factorial is equal to 9 factorial times 10. We don't even have to calculate what 10 factorial is to know that. And so we have just 10. In general, how can we calculate n choose k reasonably fast? Because we really don't want to have to calculate all these factorials. Certainly for something like 10. 10 is a big factorial. For example, what is 10 choose 3? We know that this is 10 factorial over 3 factorial times 7 factorial, but I don't really want to calculate this division. How can we do it faster? Exactly, we can cancel some things out. Let's cancel some things out by, we know that 7 factorial is pretty big and 10 factorial is pretty big, so let's try to get rid of both of them. We know that 10 factorial is equal to 10 times 9 times 8 times 7 factorial, whatever 7 factorial is. So we just write that out. 10 times 9 times 8 over 3 factorial. Now 3 factorial is just 6, it's 3 times 2 times 1. So 10 times 9 times 8 over 6 is much more manageable. We can divide the 10 by the 2 in the 3, and the 2 from the 6. We can divide the 9 by the 3 from the 6, and we get 5 times 3 times 8, which is just 120. And in general, we can see how the way to do this is basically, instead of doing n over n minus k factorial, we can do n times n minus 1 times n minus 2 with k different terms here. We can do, here there are 3 different terms over 3 different terms. 10 times 9 times 8 over 3 times 2 times 1. If this were 10, choose 4, we would have 10 times 9 times 8 times 7 over 4 times 3 times 2 times 1. Or 10 times 9 times 8 times 7 over 4 factorial. This just makes it easier to calculate these things. You can do it by hand, at least for things like 10 choose 3. What about n choose n minus k? So from this formula, we can see that n choose n minus k is equal to n factorial over n minus k factorial times k factorial. But this looks very similar to this. We just swapped around the 2 terms in the denominator. So that doesn't actually change anything, which means it's equal to n choose k. Okay. Why is this the case intuitively? So this is algebraically, we just showed algebraically this is true. Why is this the case intuitively? Remember that n choose k is the number of ways to pick k things from a set of n things. Yeah, we can think of it as the number of things to leave out. We can choose either which k things to include or which n minus k things to exclude. That means that they're just equivalent. This is sort of a combinatorial argument. This is the algebraic argument. This is the combinatorial argument. Interpreting the meaning of the binomial coefficient as actually, what's going on with choosing stuff. Okay. How many ways are there to divide a group of 6 people into group A, group B, and group C? Starting problem. Yes, you can have an empty group. The groups could be any size. Some disagreement? So we don't know the sizes of these groups. They don't have to be equal. Yeah, so each person has 3 options in this case, so 3 to the 6. 3 for the first person, 3 for the second person, so on. It's just 3 to the 6. Okay, that didn't actually use binomial coefficients. Now, how about you make sure that the groups are a certain size? Each has to have size 2. How do you divide a group of 6 people into 3 groups, A, B, and C, each with size 2? Again, some disagreement, which is great. So let's think about it as progressively choosing this. If you're trying to do many different things, try to do it one at a time. Let's first pick group A. There are 6 choose 2 options for group A. There's how many ways to pick 2 people to go into group A. Now there are 4 people left. So picking group B is going to have 4 choose 2 options. We don't know what those 4 people are. The 4 people depended upon whom we picked for group A. But we know that there are 4 people left. So 6 choose 2 times 4 choose 2. Now there are 2 people left. So those are automatically group C. I'll come back to the question in a moment. So the overall number of ways is going to be 6 choose 2 times 4 choose 2. And if we write these out, we can see that the 4 factorials cancel. So we don't even have to work them out. We get 6 factorial over 2 factorial times 2 factorial times 2 factorial. Each of these is just 2. So it's 720 over 8, which is 90. Now there's a question. What if the groups are identical? I.e., what if you don't care about labeling them as A, B, and C, if you can permute them? Well, in that case, what happens? How do you get from our answer to the answer if the groups are allowed, if you don't care about the labels on the groups? You just want to divide them into. Yeah, you can divide by 3 factorial, which is the number of ways to rearrange those, to permute those 3 different groups. And a good way to check your work is make sure that you have an integer as an answer. If you ended up with like 90 over 7 as your answer for the number of ways to arrange anything, then you have a problem because 90 over 7 isn't an integer. But 90 over 6 is an integer, which is good. So you have 90 over 6, which is whatever it is. I'm not sure I can do the division. 15. Okay, so this is a particular case of something that's actually larger. These are called multinomial coefficients. We're not really going to get into them, but they correspond to the ways to divide up n people into a group 1 of size n1, a group 2 of size n2, up to a group k of size nk. And the number of ways to do that is n factorial over n1 factorial times n2 factorial all the way up to nk factorial. You can see that here, 6 factorial over 2 factorial, 2 factorial, 2 factorial. The 2's come from the sizes of the groups, A, B, and C. If it had been sizes 2, 3, and 1, then this would be 2 factorial, 3 factorial, 1 factorial. And notice that these always add up to n. So 2 plus 2 plus 2 equals 6. All of these have to add up to n because we're dividing up into smaller groups. And if you, what is the situation if k equals 2? What if you're only dividing into 2 groups, size n1 and n2? Yes, so these are just going to be the same as the binomial coefficients. So remember the formula that we had for binomial coefficients is just n factorial over k factorial times n minus k factorial. And so what you can think of it is dividing n into a group of k and a group of n minus k. So in the notation later on, we had n1 and n2, with n1 plus n2 equals n. So this is just a special case, actually, of the multinomial formula, multinomial coefficient formula. Questions? If we were dividing 6 people into 3 indistinguishable groups of varying size, that is a little bit more complicated because the groups might be, it is not what you suggested, which is not in fact an integer. I'll let you think about that. This whole check that something is an integer before you think of it as the number of arrangements of things, it really is helpful. I've done this so many times where I've thought I had an answer, and then I realized that it wasn't actually a whole number. Okay. Problem. How many ways are there to pick an ordered list of k things out of a set of n things? So now we have the same thing as before with binomial coefficients, but now we care about the order of the things. So for example, AB is different from BA for picking them out of the set. Yes, you can do this writing this formula P of nk. What is P of nk? Yes. Okay, so we first have to pick what the k things are. The number of possibilities is n choose k. And we've sort of already seen all this stuff. If we care about the ordering as well, then we can just look at the number of possibilities for ordering those k things. The number of possibilities is k factorial. So we can take n choose k times k factorial. And very nicely, the k factorial cancels. And we get something that's even simpler, which is n factorial over n minus k factorial. Okay. So sometimes, somewhat frustratingly, these are called permutations, and the binomial coefficients are called combinations. I don't like this because it allows you to get confused by the number of permutations of a thing. And a permutation should really be how many ways are there to permute n different things or k different things. But yes, some people call these things P of nk. They are in general much less useful than the binomial coefficients, so we won't be really looking into them. Binomial coefficients come up all across mathematics. Okay, so let's get to one of the most beautiful things about binomial coefficients, which you may have seen before, which is Pascal's triangle. This is an infinite triangle. This is just the first few rows of it. There are more rows, infinitely many more rows, and this is just the binomial coefficients arranged in a triangle, n choose k. So this is the 0th row. This is the first row, second row, and so on. And the 0th entry in the, so for example, this is the second entry in the 5th row. 0, 1, 2, 3, 4, 5, 5th row, 0, 1, 2, second entry. Go down like this, go across like this. Second entry, 4th row, second entry, 3rd row, third entry, 4th row, third entry, 5th row, and so on. Okay, what are some properties that we see here? Well, we can see, first of all, that n choose 0 is going to be equal to 1. That's just the first element of each of these rows. Remember, we already noticed that n choose 0 should be 0. N choose n is the last element of each of these rows. That should also be 1. And n choose 1 should be n. 1, 2, 3, 4, 5, 6, 7, so on. You can imagine that all these other things are 0 too. You can imagine that it's sort of infinitely extending in all directions with the thing up here being 0 if you want. It's symmetric. If you flip it around this middle, you get the same thing. 1, 6, 15, 20, 15, 6, 1. 1, 5, 10, 10, 5, 1. And that's because n choose n minus k is equal to n choose k, which we've already seen. So these are properties that we already knew should exist in this triangle. But there's more. There's a lot more here. And you can just keep on listing cool properties of Pascal's triangle. I will list just a couple of them. The most important thing, probably, the thing that people often learn is each number is the sum of the two directly above it. So for example, 3 is the sum of 2 and 1. 4 is the sum of 3 and 1. 10 is the sum of 6 and 4. 20 is the sum of 10 and 10. 35 is the sum of 20 and 15. Whoop, that's cool. In particular, what does that mean for this second column, i.e. n choose 2? If this property is true, which we will prove in a moment. What does that mean for this second column? 1, 3, 6, 10, 15, 21. Does anyone recognize those numbers? These were just ones. These are just 1 through n. They are not the Catalan numbers, unfortunately. The difference is increasing by 1, yes? Yeah, so these are the numbers that we saw before, the triangular numbers, adding up the integers 1 through n. Or in this case, actually 1 through n minus 1. So this is the fourth row, and this is 6. That is the third triangular number. They're offset by 1. So this is 3 plus 2 plus 1. This is 4 plus 3 plus 2 plus 1. This is 5 plus 4 plus 3 plus 2 plus 1. Now, why is that the case? How can we prove immediately, assuming this, that these are indeed the triangular numbers? Due to this property, it's basically an induction proof, right? Like these things are just 1 through n. So here, if we start out with a first triangular number, 1, we add 2 to it here, we add 3 to it here, we add 4 to it. And the reason why we're adding 4 to it is because of this property where this is the sum of the two immediately above it. We know this one is going to be 4, we know this one is going to be the third triangular number. 5 plus this, and 6 plus this, plus 7. Okay. Now, let's actually prove this thing. Thank you, that's something I didn't know. Comment that the triangle is also accredited to Cayenne, and it can also be called the Cayenne-Pascal triangle. I did not know that. I definitely, I feel bad for not knowing that. There is very European-centric naming of a lot of these things. There's also very America-centric naming of various things. When we get to algorithms, a lot of the things will have been discovered independently and earlier by Russians, but they were published in Russian or Soviet journals and were not talked about in America. Okay, let's prove this thing, which is called Pascal's identity. Now, first of all, let's just convince ourselves that this is in fact what we're trying to prove, right? Like, so here we're trying to prove that the kth element of the nth row, so like 35, is equal to the sum of the two things above it, which are both in the previous row. So n minus 1, previous row. Which two elements? Well, the kth element, which is this one, 20, and the k minus first element, which is 15. So 35 should be equal to 20 plus 15. This is an example of what we're trying to prove. Okay, so why is this true? What are a couple of different ways to do this? First, go for an algebraic proof using formulae. Start you out. Expanding them, yeah? So this is, we know the formulae are n minus 1 factorial over k minus 1 factorial times n minus 1 minus k minus 1 factorial. Ugh. N minus 1, and then the second one is n minus 1 factorial over k factorial, because we're choosing k, times n minus 1 minus k factorial. Okay, so why does this, how do we do something with this? We can just simplify it a little bit. What do we do now? What's the next step we could take? Yep, common denominator. Okay, so what is the common denominator? Well, k factorial is equal to k minus 1 factorial times k. So this first thing, can be k over k factorial. It's 1 over k minus 1 factorial. Now the second thing is n minus k minus 1 factorial. Ugh, it's a little bit painful, but this is equal to n minus k over n minus k factorial. Because if you cancel the n minus k, then you just get n minus k minus 1 factorial. Okay, so now they have a common denominator. What do we do now? Rearrange the terms in the numerators. N minus k plus k times n minus 1 factorial, n times n minus 1 factorial, boom, we're done. Because this is exactly the formula for n choose k. Okay, that was an algebraic proof. Let's do a combinatorial proof. What's a combinatorial proof? Interpreting these as ways to choose people from a group, say. And consider picking a group of k things from n things. Yep, so there's been a suggestion to divide into cases whether we choose the nth element or not. Or in this, I wrote down whether we choose the first thing or not. What happens if we pick the first thing? How many ways are there for choosing the remaining things? So we have k minus 1 things remaining to pick. And we have n minus 1 things to pick them from because we already got rid of the first thing. Okay, so that's going to give us the number of ways to pick a set which contains the first thing. But many of our sets will not contain the first thing. If we don't pick the first thing, then we have to pick all k things from the other n minus 1. And that's going to give us the number of ways to choose k from n minus 1. So the total number of ways to pick k things is the number of ways to pick the first one and then pick the other k minus 1 from the remaining n minus 1. And the number of ways to not pick the first one and pick all of the k from the final n minus 1. Since this divides up the different ways of doing this, we have this equality. No algebra necessary. Questions? Okay. So here is why they are called binomial coefficients. The binomial theorem says that if you expand x plus y to the n, you get this. This is a polynomial in multiple variables, x and y. This first coefficient is always going to be 1, so we're always going to have x to the n. And this is also going to always be 1, so you have y to the n. These other things are a little bit more complicated. Let's do some examples. When I'm doing examples or working out binomial coefficients in general, I often will do Pascal's triangle. I'll be like, okay, so 1, 1, 1, and now I just find all the others by just adding them up. I'm like, okay, here's I know there's going to be another 1 here. The 2 is just 1 plus 1, 1. 1, 1 plus 2, 3. 2 plus 1, 3, 1. It's really easy to work all these things out quickly just by adding things up. So here I've gotten to 1, 4, 6, 4, 1. That's the fourth row, so it's n equals 4. So some examples of how we can use the binomial theorem. X plus y to the fourth is going to be x to the fourth plus 4 is the first coefficient. 4 choose 1. 6 is the second coefficient. 4 choose 2. 4 choose 3. And 4 choose 4. Here's a special case if I take y equal to 1. x plus 1 to the fourth. This will often turn up doing x plus 1 to the sum power. X to the fourth plus 4x cubed plus 6x squared plus 4x plus 1. X minus 1 to the fourth. Same thing, just y is equal to minus 1. So y is negative 1, y squared is positive 1, y cubed is negative 1, and so on. So it's just the same as this, except these signs are alternating. Y plus 2 to the fourth, it's going to be the same as this, only we've substituted 2 in for y. So here we get 8, here which is 4 times 2. Here it's 6 times 2 squared, which is 24. Here it's 4 times 8 times 2 cubed, which is 32. And then finally we get 16 at the end, which is 2 to the fourth. So these are some examples of how you could use the binomial theorem. Question? And this is why they're called binomials. So binomial means literally two names or two variables. So this is just like saying this is a binomial expansion, two variable expansion. Multinomial coefficients, which we saw before, were if you had x plus y plus z, or w plus x plus y plus z, or in general k different variables. And you can go back and see that actually there is a multinomial theorem, which is basically the same as this, except that the coefficients correspond to those other ways to partition a set into smaller sets. Now, how do you prove this thing? Why is it true? As an outline, x plus y to the n is going to be equal to, and let's just expand out, there are n different copies of x plus y. So now the number of x to the k, y to the n minus k terms that you get is just the number of choices for which x plus y's contribute the x, which contribute the y. You get to choose. Imagine you're trying to pick something with an exponent of k on x. You have to pick k of these to contribute the x, and the other n minus k will contribute the y. So it's a choice of k out of n total to be the x, and n minus k to be the y. Alternatively, it's a choice of n minus k to be the x, and choice of n minus k to be the x, and choice of k to be the y. Because n choose n minus k is equal to n choose k, you can think of it both ways. Here's an example. If you have x plus y cubed, you can write out all the arrangements of the x's and y's. You're going to have a bunch of different terms, which all sum together. So here you have x multiplied by x multiplied by x, y multiplied by x multiplied by x, x multiplied by y multiplied by x, and so on. These are all the different possibilities. There are two possibilities for each of these three things. Now, how many things are you going to get with x squared y? Well, you're going to have to pick two x's and one y. How many ways are there to arrange two x's out of a set of three things? Well, it's going to be 3 choose 2, or alternatively 3 choose 1. Because 2 plus 1 is 3. So n choose k is equal to n choose n minus k. Questions? There's a question about using proof by induction and possibly using Pascal's identity. This is a beautiful way to prove this. If you imagine doing this by induction, assume that this thing is true, the binomial theorem is true, and imagine multiplying everything by x plus y. Now, what will you get for a term in the middle? Well, two terms will contribute to the next term. For example, what is going to be the term which is x to the n minus 1 times y squared? Well, that's going to be this term times y plus this term times x, which means the coefficient on it is going to be n choose 1 plus n choose 2. And by Pascal's identity, we know that that is going to be equal to n plus 1 choose 2. If you didn't get that, don't worry. This is basically just saying that you can use Pascal's identity and induction to prove the binomial theorem really smoothly. It gets a bit thorny in the notation, but that's just the only thing. It's just like a few additional indices. More questions? Okay. So, prove that the sum of the different binomial coefficients from 0 to n is equal to 2 to the n. Yeah, so there are a couple of different ways to do this. One is using the binomial theorem. We know that x plus y to the n is equal to this thing. How can we get from this sum to the sum we want? As people are suggesting, we can set x equals 1 and y equals 1. That means that all of these things, the x's and the y's, will all disappear. And on the right-hand side, we'll have just exactly this, the thing that we want. On the left-hand side, we will have 1 plus 1 to the n. And that's 2 to the n. Very, very fast. There's another fast solution, though, too. Combinatorial solution. What the sum is that we're looking at is the number of ways to pick a subset of size 0, plus the number of ways to pick a subset of size 1, plus and so on, plus the number of ways to pick a subset of size n. What is this? Yeah, it's just the number of subsets, or you can, if you're fancy, you can call this the power set. The number of ways to pick a subset of any size. Now, how many ways are there to pick a subset of any size? So it's the number of subsets of a set of size n, which is 2 to the n. Because each element of the set of size n could either be in the subset or not. 2 possibilities for each of the n elements means that you have 2 to the n possible subsets. Question? Okay, question. If you flip a fair coin 6 times, what are the odds of getting at least 4 heads? Let's go through a bit of it. How many ways are there to get exactly 4 heads? For example, that's a way to get 4 heads. Oh, by the way, the question was, what are the odds of getting 4 heads? Not number of ways to get 4 heads. We can start out with a number of ways to get exactly 4 heads. So here, how many ways are there to get 4 heads? Well, it can be 6 choose 4, and you're picking 4 of the 6 flips to be the heads. Likewise, 6 choose 5 for 5 heads, and 6 heads is 6 choose 6. How many total ways are there for flipping heads and tails? Yeah, 2 possibilities for each flip, so 2 to the 6 overall. So the overall answer is going to be 6 choose 4 plus 6 choose 5 plus 6 choose 6 over 2 to the 6. And to make that easier to calculate, you can flip these. 6 choose 4 is equal to 6 choose 2, 6 choose 5 is equal to 6 choose 1, and 6 choose 6 is equal to 6 choose 0. So that is going to be this plus 6 plus 1 over 2 to the 6. If you simplify that, it'll come to 11 over 32, which is a bit more than 1/3 probability. Now, you might notice, you can also think of the denominator as the number of ways to get 0 heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads, or 6 heads. And that's because the sum of all the binomial coefficients is equal to 2 to the n. Oops, sorry. Okay. Now let's do our final problem, the thing we saw at the beginning. You have m identical balls and a row of n labeled buckets. How many ways can you put the balls in the buckets? Buckets are allowed to be empty. We can tell the difference between the buckets because they're labeled. It matters what order the buckets are in. The balls are identical. It doesn't matter how we arrange them in the buckets. It is different from what we did with the groups. Now, the reason is because before, the people were distinguishable. Here we have balls that are totally identical. This will come up a lot. Let's try a small example. 6 balls, 3 buckets. Some video is suggesting we can write it out like, here are some balls. Then I'm just going to put a divider to the next bucket. Here's a ball. Here's another divider, and here are the rest. The dividers are between different buckets. So this, for example, would represent 3, 1, 2. Okay. More examples. 2 dividers followed by 6 balls is actually going to represent 0, 0, 6. 2 balls, 1 divider, 4 balls, 1 divider represents 2, 4, 0. Okay. Notation is sometimes really, really useful in solving a problem. How does this help? Any observations? Seeing a lot of disagreement in the answer here. So there will always be 8 things in this particular case. They will either be dividers, or there will be these O's, balls. And there are going to be 2 dividers, and there are going to be 6 balls. So how many ways are there to arrange this situation? And something that's important is not only do we have this, but also every order of 2 dividers and 6 balls is a legal arrangement of balls. How many ways are there to arrange just in the case of 6 and 2? We have 8 things. We know that 2 of them have to be dividers, and the other 6 have to be balls. But we don't know which are which. How many ways are there to choose out of the 8 things, 2 to be dividers and 6 to be balls? It is just 8 choose 6, or 8 choose 2 alternatively. Whoop. I know my mind was blown when I first saw this. So what's it going to be in general? You have m balls, n buckets. So there's a question about the dividers being identical. The dividers are identical, but we know that everything that comes before the first divider is the first bucket. Everything that comes between the first and second is the second bucket, and so on. So how many dividers do we have? Well, we're going to have n minus 1 dividers. We're going to have n balls. So in general, we're going to have m plus n minus 1, choose m. There are m balls, n minus 1 dividers. We have to choose which of them are balls and which of them are dividers. Let's do a sanity check with this answer. Let's plug in a simple value. Let's say there's just one ball. One ball, n buckets. 1 plus n minus 1, that becomes n. N choose 1. N choose 1 is n. There are n ways to put one ball into n buckets. Good. It's definitely true. You can also try various other things, like there's just one bucket. In that case, it's m plus 1 minus 1. Choose m. So m choose m, that's just 1. That's good. There's only one way to put all the balls in one bucket. Okay, and we're done. So that is a really beautiful answer to a problem that doesn't seem like it should have a simple closed form answer. Now is office hours time, and next time we will be talking about graph theory. Thanks all for coming. For those of you who didn't catch, actually, before you go, I just want to get a quick poll about the speed of today's class. And I would also, for those of you who didn't hear the start, the problem set will soon be released, but it is probably, I think it will be due a week after you might have expected, which is October 9th, so that the Iclear deadline, for those of you who are submitting to the Iclear conference, is not a problem. And also so that you can have a peaceful Thanksgiving break without dealing with a PSET. But the PSET will soon be out, so you can work on it earlier if you want. Okay, thanks everyone, and stick around for office hours if you'd like.